Welcome, and thank you for joining me on this gentle journey. Make yourself comfortable and allow the day's worries to drift away. In this calm and quiet moment, we will explore the soothing world of waves, electricity, and magnetic fields. There's no need to focus too hard, just listen softly, let the words wash over you, and feel free to drift towards sleep as you absorb these ideas. We will take our time and move slowly. Let's begin with a deep breath and imagine ourselves floating on a peaceful sea of knowledge, where each gentle wave, each subtle spark, and each soft magnetic pull guides us into a state of deep relaxation. Take another slow breath in and out. Picture yourself by the shore of a calm lake at dusk. The water is smooth like glass and the air is still. Now, a small, gentle breeze begins to blow, and tiny ripples form on the surface of the water. These ripples travel outward, spreading in widening circles. They are small waves traveling quietly across the lake. You watch as they glide by, one after another, carrying a bit of energy with each rise and fall. In this tranquil scene, we find the first of our topics: waves. Waves are all around us. Some we can see, like the water waves on a lake or ocean. Others we can only feel or hear, like the soft sound of wind or the distant hum of a singing bowl. But what exactly is a wave? In the gentlest terms, a wave is a repeated, rhythmic motion that carries energy from one place to another without carrying along matter permanently. Think of that quiet lake. When the breeze creates ripples, the water itself isn't moving across the lake in a rush. Instead, it's the shape, the rise and fall, that is moving. The water particles bob up and down in place, allowing the wave pattern to travel onward. If you were floating on your back in the lake, you would feel yourself lifted gently up and then set back down as the wave passes. But you wouldn't be dragged along with the wave. The energy of the wave moves through the water, while the water mostly stays where it was, simply oscillating, that is, moving back and forth around a resting position. In this way, waves let energy roam freely through a medium, be it water, air, or a stretched rope, without carrying the material of that medium along for the ride. Let's picture another scene. Imagine you have a long, soft rope or a ribbon laid out across the grass on a summer evening. You hold one end and give it a slow, gentle flick up and down. A ripple travels along the rope, a wave moving towards the far end. The rope itself isn't being thrown forward. Instead, a bump, a shape, moves through it. That bump is a wave on the rope. This type of wave is called a transverse wave. The word transverse means that the motion of the medium, the rope in this case, is perpendicular to the direction the wave travels. When you flick the rope up and down, each bit of the rope moves up and then down perpendicular to the rope's length, while the wave travels horizontally along the length of the rope. The rope's particles, imagine the tiny fibers, simply move up and down locally, and the wave's energy flows along sideways. If you had painted a small mark on the rope, you would see it go up and then down as the wave went by, returning roughly to where it started, not flying off to the end. Now consider a different kind of wave, one we encounter every day: sound. You are listening to my voice right now, and what you're hearing is carried to you by sound waves in the air. If you could see these sound waves, though they are invisible, you'd find that they are a different type, known as longitudinal waves. In a longitudinal wave, the motion of the medium is parallel to the direction of the wave's travel. Instead of moving up and down, the particles of the medium, like air molecules, move back and forth in the same direction the wave is going. How does this carry sound? Imagine a small tuning fork gently struck in a quiet room. As it vibrates, it pushes on the air next to it, compressing the air molecules slightly and pulling back and letting them spread out. This creates regions of slightly higher pressure, where molecules are a bit closer together, followed by regions of slightly lower pressure, where they're more spread out. These regions travel outward as a pattern, a wave of compression moving through the air. When that wave reaches your ear, those compressions and rarefactions, spreads, make your eardrum vibrate in and out, and you perceive sound. In this case, each little parcel of air just oscillates back and forth in place, crowding a bit, then separating, passing the energy along to its neighbour. Again, the air itself doesn't rush across the room to your ear, only the disturbance, the pattern of pressure changes, moves forward. Sound waves, then, are longitudinal waves, where the motion of the medium is along the line of travel, like a gentle pulse of push and pull. It's beautiful to think that whether it's a ripple on a pond or a whisper from across the room, the essence is the same. Waves carry energy without carrying along material. A water wave can deliver a subtle push to a floating leaf, causing it to bob gently. A sound wave can carry the soft melody of a lullaby across a bedroom. In both cases, something is transferred: energy, information, a signal, yet the medium, water, air, mostly stays in place, simply moving rhythmically to let the energy pass. Let's deepen our understanding of waves by considering their basic features, but we will do so slowly and calmly. Think again of a simple wave on a rope. As the wave travels, the rope forms a repeating pattern of crests and troughs. A crest is the highest point of the wave, where the rope is lifted the most, and a trough is the lowest point, where the rope dips the deepest. The amplitude of the wave is the height of the crest, or depth of the trough, from the rope's resting position. In our gentle rope flick, perhaps the rope rose only a small amount. That means a small amplitude, a gentle wave. If one were to whip the rope harder, not that we need any sudden motions in our peaceful setting, the crests would be higher and troughs deeper. A larger amplitude, a more energetic wave. Amplitude is related to the wave's energy. A big wave carries more energy than a small one, just as a taller ocean wave packs more energy than a tiny ripple. Now consider how far apart the crests of the rope wave are. This distance between successive crests, or between troughs, is called the wavelength. Perhaps on our rope, the crests are a couple of feet apart. In the lake example earlier, you might notice the ripples have a certain spacing. That's their wavelength. Wavelength is one of the fundamental characteristics of a wave. It's essentially how long one cycle of the wave is in space. Another gentle concept is the frequency of a wave. This describes how often the crests pass by a given point per second. If you wiggle the rope slowly, only 1 or 2 crests might pass a fixed point on the rope each second, a low frequency. If you wiggle it a bit faster, still gently, more crests pass per second, a higher frequency. We measure frequency in cycles per second, a unit called hertz, but you don't need to worry about numbers. Just think of frequency as the pace or rhythm of the wave. A slow, steady rhythm is a low frequency, and a quick patter is a high frequency. These properties, wavelength and frequency, are connected by the wave's speed. Imagine watching a leaf floating on the lake as waves pass. If the waves are spaced far apart and arriving slowly, the leaf will bob infrequently and the wave might be slow moving. If the ripples are close together and frequent, the wave likely moves faster. In fact, a wave's speed is simply how quickly a crest travels forward, and it turns out that the speed is equal to the wavelength times the frequency. In simple terms, if crests are far apart but coming very often, the wave moves quickly. If they are far apart but rare, the wave moves more slowly. But let's not get lost in equations. We can keep it intuitive. Think of gently tapping one end of a long stretched ribbon at a regular pace and watching the pulses glide to the other end. If you tap faster, the pulses chase one another more closely and reach the end sooner. If you tap slowly, each pulse has more space and arrives later. Thus, the interplay of frequency and spacing, wavelength, sets how fast the energy goes along. Now, different mediums carry waves differently. A medium is what the wave travels through: water, air, a rope, or even solid ground. Each material has its own properties, how heavy it is, how stiff or stretchy it is, that determine how fast waves can move in it. For instance, have you ever noticed that if you put your ear to a metal railing and tap it, the sound reaches you faster through the metal than through the air? Or perhaps you recall seeing lightning in a storm and hearing the thunder after a delay. Light travels extremely fast. Essentially, in a vacuum, it's the fastest thing there is, whereas sound in air is much slower, about 340 meters per second, roughly 750 miles per hour. In water, sound travels faster than in air, around 1,500 meters per second, more than 4 times quicker than in air, because the water's particles transmit the pressure changes more readily. And in steel, sound waves travel faster still, maybe 15 times the speed in air, since the metal is rigid and connects the vibrations efficiently. You don't need to remember the numbers, just imagine the idea: different materials, different wave speeds. A gentle tap on a table travels swiftly through the solid wood as a sound wave, while that same tap sound moving through the air is slower. Even within one medium like air, not all waves go at the same speed, but for our purposes, we'll consider the basics. There are also media that can support different kinds of waves. Solids, for example, can carry both transverse and longitudinal waves. In an earthquake, for instance, the ground can experience longitudinal pressure waves and transverse shear waves, but a liquid like water or air can't sustain transverse shear waves through its bulk because fluids don't resist shear. Imagine trying to shear or twist a liquid, it just flows. So in fluids, the waves are mostly longitudinal, pressure waves. The waves in the ocean are a special case. On the surface of water, we get a mix of motions, mainly up and down, transverse, with a bit of back and forth, but deep underwater, sound travels as purely longitudinal pressure waves. If this feels a bit technical, don't worry, just picture that different substances allow different wave motions. A rope or a stretched string loves to carry transverse waves, the up and down flicks. Air and water primarily carry longitudinal waves, sound and pressure pulses. A metal rod can carry both. You could send a pulse of compression along it or whip it so it vibrates sideways. Let's return to a more tangible image to reinforce these concepts calmly. Envision a slinky, one of those long helical springs resting on a smooth floor. If you anchor one end and give the other end a quick push and pull lengthwise, you'll see a compression wave travel down the spring. Coils bunch up in one section and that compressed region moves along to the far end. That's a clear example of a longitudinal wave. The coils moved in the same direction the wave went along the spring. Now, if instead you shake one end of the slinky slightly side to side, perpendicular to its length, you can send a kink or wiggle down the spring, a transverse wave moving down while each coil moves side to side. The slinky can support both types of waves because it's a springy object that can compress and bend. Watching such experiments in your mind, you can appreciate the diversity of wave behaviors in a very calm, visual way. Waves also have an interesting way of interacting with boundaries, like the end of the rope or the edge of the pond. When a wave encounters an end or a different medium, part or all of it can reflect, meaning it bounces back. If you've ever shouted into a large empty room or across a canyon and heard an echo, that's a sound wave reflecting off a distant surface and coming back to your ears after a short delay. In our rope scenario, if the far end of the rope is tied to a post, a fixed end, the wave inverts when it reflects. The crest comes back as a trough. If instead the rope's end is free, say the rope is just loosely tied or held so it can move, the wave might reflect without inverting. The crest comes back as a crest. These are details one might learn in physics class, but here we can simply imagine that waves, like polite visitors, bow and turn back when they meet a boundary. Picture those lake ripples we started with as they reach the pond's edge, perhaps the water's edge or a rock. New ripples turn back towards the center of the pond. If someone were watching from above, they'd see a pattern of outgoing and incoming ripples overlapping. This brings us to another gentle but fascinating behavior of waves, superposition or interference. When two waves meet, they combine their effects. Because waves are essentially disturbances, they can pass through each other. For a moment while they overlap, the resulting wave is the sum of the two. If two wave crests arrive together, they add up to a taller crest. This is called constructive interference. If a crest and a trough arrive together, one trying to lift the medium up and the other trying to press it down, they can cancel each other partly or even completely. So that's destructive interference. But note, this cancellation is only while they overlap. After passing through each other, the waves emerge on the other side unchanged, as if nothing happened, continuing on their way. It's like two breezes crossing. They pass through and each breeze carries on. In a very calm pond, you might see this if you drop two pebbles in at different spots. Their ripples spread, and when the ripple patterns meet, you briefly see a new pattern of higher and lower water surface. Then they proceed outward. In sound, interference can lead to interesting effects too. If two gentle sound sources, like two speakers playing the same soft tone, are arranged just right, in some places their sound waves may reinforce each other, and in others, they may partly cancel, creating quiet spots. But you don't need to worry about the complexity. The key idea is that waves can overlap and combine in the medium, creating a new resulting wave pattern that is the sum of them at that moment. A particularly soothing and important result of interference is the creation of standing waves. Unlike traveling waves that move along, a standing wave appears to stand in place, oscillating in a fixed region. How does that happen? Imagine again our rope, tied at one end to a post. If you send a continuous series of waves down the rope, say by moving your hand up and down rhythmically, those waves will travel to the end and reflect back. Now, if you jiggle the rope at just the right frequency, a special frequency where the incoming and reflecting waves align in a certain way, the rope will form a steady pattern of loops that seem to just oscillate in place. At certain points along the rope, called nodes, the rope barely moves at all. These points are calm, always at rest position. At other points, called antinodes, the rope swings up and down with maximum amplitude. The pattern doesn't seem to travel, it just sits there waving in place. This is a standing wave. You may have seen this if someone plays a guitar. When a string is plucked, a standing wave forms on the string at particular frequencies, producing musical notes. The string's ends are fixed, so only certain wavelengths fit on the string, such that an integer number of half wavelengths spans the length with nodes at the ends. The result is a pleasing, steady vibration. Even if you haven't seen a string in slow motion, you've likely heard the result, a stable musical tone. It's amazing that out of all the chaotic motions that could happen, the string naturally favors these harmonious standing patterns, each corresponding to a particular frequency or pitch. You can think of standing waves as arising from interference between two waves traveling in opposite directions, the original and the reflected. When just right, their interference produces that stationary pattern. In a calm way, nature finds a resonance, a frequency that works with the system's boundaries, and energy flows into that pattern easily. Resonance is why pushing a swing at just the right rhythm makes it go higher. Similarly, shaking a rope at the right rhythm sets up a large oscillation. We find waves not only in obvious places like water and sound, but also throughout nature. The gentle sway of a tree in the breeze is a wave in its branches. The nearly invisible vibrations of a spider's web when a tiny insect lands, those are waves traveling along the silk, alerting the spider. Even within our bodies, waves occur. For example, seismic waves from gentle footfalls or movements travel through our flesh and bones in tiny ways. Or consider brain waves, electrical waves of activity sweeping across neurons. We'll speak more of electrical phenomena soon. The calm beating of your heart sends a pressure wave through your arteries. Your pulse is essentially a wave propagating along blood vessels. And at the largest scale, we have gravitational waves, ripples in space-time itself. But those are extremely faint and far beyond daily experience, not something to concern ourselves with as we drift to sleep. As you lie here listening, you're also immersed in countless unseen waves. If your window is open on a summer night, faint sound waves of crickets chirping might be coming in. Light from the moon, which is a form of wave, an electromagnetic wave, is gently falling through the window. Even if everything is quiet and dark, you are bathed in the ever-present whispers of radio waves carrying distant communications, and the earth gently hums with seismic waves far below our threshold of feeling. We are truly in a sea of waves at all times. But don't let that thought be alarming. These waves are usually so subtle and natural that we live in harmony with them. Now that we have spent some time with the concept of waves, let's gently recap the key points. Waves are oscillations, repetitive motions that carry energy. They can be transverse, like the up and down motion of our rope or water wave, or longitudinal, like the back and forth compression of sound in air. They have amplitude, strength, wavelength, spacing, and frequency, timing, which together set how they move. Waves pass through media, reflect off boundaries, interfere with each other, and can form quiet, steady patterns like standing waves when conditions are right. All of this happens quietly, naturally, as if the universe loves to wiggle and flow. You don't need to remember any terms if they seem too much, just remember the gentle images. The bobbing leaf on the pond, the rope's ripple, the soft whisper across the room. Waves are nature's way of sending out a message or energy, often in the most graceful manner. Allow yourself to imagine these waves for a moment. You might picture lying on a raft in a calm bay, feeling the very slow rise and fall as distant swells pass by underneath. Each swell lifting you slightly, then lowering you. They come regularly, and you relax more with each gentle motion. Or perhaps you visualize yourself in a cozy room, listening to slow, relaxing music. The sound waves carry the music to your ears, an invisible, comforting visitor, and the rhythmic sound helps you drift to sleep. Waves connect us with the world, bringing us light and sound, carrying the energy of touch and warmth. In a way, life is immersed in waves. Feel how calming it is to know that even the dynamic processes of nature can be described in such a flowing, peaceful way. You are part of this gentle motion. Your breathing is like a wave, in and out, rhythmic and life-sustaining. As we move on, keep that sense of gentle rhythm with you like a background lullaby. We will now transition softly to our next topic, the realm of electricity, a different aspect of nature's story, yet deeply connected to waves in time. Take a slow breath, and let's quietly step into the world of tiny charges and silent electric fields. Think of a moment on a cold, dry day when you might shuffle across a carpet and reach for a metal doorknob. There's a tiny spark, a little snap, and you feel a sudden small shock on your fingertip. It's a brief, harmless zap of static electricity. Now, in the spirit of our calm exploration, instead of finding that startling, let's examine it curiously but gently. What caused that spark? It was the movement of electric charge jumping between you and the doorknob. Electricity, at its heart, is all about charges and how they move or interact. So what is electric charge? It's a basic property of certain particles of matter. You may recall that atoms, the tiny building blocks of everything around us, contain even smaller particles, protons, neutrons, and electrons. Protons carry what we call a positive charge, electrons carry a negative charge, and neutrons have no charge. Opposite charges attract each other, much like two opposite poles of magnets, which we will discuss later. And like charges repel each other. This means two electrons, both negative, push away from each other. Two protons, both positive, do the same, but an electron and a proton, negative and positive, will pull toward each other. In everyday objects, there are huge numbers of these charged particles, but normally they're balanced, equal positives and negatives. So overall, things are neutral and there's no obvious electric effect. However, if this balance is disturbed, interesting things happen. Consider the case of shuffling on the carpet. As your socks rub against the carpet fibers, tiny charged particles can be transferred. You might accumulate an excess of one type of charge on your body. Let's say you pick up extra electrons, giving you a slight negative charge overall. The doorknob connected to the building might be more neutral or even slightly positive relative to you. When you reach out, the difference in charge causes electrons to suddenly leap across the small gap from your finger to the metal knob, since metal conducts electricity well, unlike the insulating carpet. That sudden movement of charge through the air is the spark you see and the shock you feel. It's a minuscule lightning bolt on a very small, safe scale. And just like that, the imbalance is corrected. Your excess electrons have flowed to the knob and into the environment, restoring balance. This little scenario illustrates a few key points about electricity. Charges can be transferred by contact or rubbing. Charges exert forces on each other. Your negatively charged hand was actually attracting positive charge or repelling negative in the knob even before the spark, drawing charge towards you. And when allowed, charges will move to neutralize imbalances. That movement is electric current, albeit a quick, momentary one in this case. Let's slow down and examine the concept of electric force and electric fields in a calm way. When you have a charged object, say a small plastic comb that you've run through your hair, picking up a bit of negative charge, that charged comb can attract neutral objects by inducing a separation of charges in them. Perhaps you've seen a charged comb pick up tiny pieces of paper. It can also attract a positively charged object or repel another negatively charged object. We often describe this interaction by saying the charge creates an electric field in the space around it. An electric field is an invisible influence extending outward from a charged object that will exert a force on other charges placed in that space. If you could visualize it, you might imagine gentle lines radiating out from a positive charge or converging inward toward a negative charge, representing how a tiny positive test charge would be pushed or pulled. But we won't worry about the diagrams. Just imagine that a charge affects the space around it, almost like how a scented candle fills a room with its aroma, just as an analogy. Any other charge that comes into that space smells the influence and feels a push or pull. The idea of the electric field is very soothing in a way. It means that objects don't have to touch to interact. A charged balloon on the wall can stay up because its field influences the charges in the wall's surface, pulling the opposite charges near and holding itself in place. When your hand was charged from the carpet, the electric field from your hand reached the doorknob before you even touched it, causing charges in the metal to rearrange slightly. Electrons in the metal were repelled away from the side near your hand if your hand was negatively charged. The air between had to break down, which it did in that spark, for charges to finally move across. Let's consider a more continuous and gentle scenario of charge and field. Imagine two tiny specks of dust in a sunbeam, each carrying a small static charge floating slowly in the air. If they have like charge, say both negatively charged, they will very subtly push each other away. If one is positive and the other negative, they will drift toward each other. They dance in the air under this electric influence, an invisible hand guiding their motion. This is Coulomb's law in action, the rule that electric force depends on the amount of charge and the distance, with unlike charges attracting and like charges repelling. We won't bother with the formula, but intuitively, the more charge, the stronger the push or pull. The farther apart, the weaker the effect, dropping off with distance. It's not unlike gravity in some respects. Gravity always attracts and weakens with distance too, but electric forces can both attract and repel, and they are often far stronger than gravity at small scales. In fact, the reason you're not falling through your chair right now is not the chair's gravity. It's the electric forces between the atoms in your body and the atoms in the chair, repelling each other strongly enough to hold you up. Almost all the tangible pushes and pressures we feel in daily life, touching a table, a breeze against your skin, the rigidity of solid objects, come down to electric forces at the microscopic level. It's quite poetic. The solidity of the world is due to countless tiny electromagnetic interactions working in harmony to create a stable environment for us. Now, when charges are not just sitting still but moving, we enter the realm of electric current and circuits, which is another facet of electricity. Let's approach this gently. Picture a calm winter night inside a cozy cabin. There's a soft lamp glowing warmly on a table. The lamp is lit by electricity flowing through its filament. Now, this electricity is a steady current supplied by a simple circuit, perhaps a battery or the mains if connected to a grid. A circuit is essentially a closed-loop path that charges travel through. The charges in question in metal wires are electrons, tiny negatively charged particles. In the metal of the lamp's wiring and filament, electrons are free to move from atom to atom. When the lamp is switched on, an electric field is established in the circuit almost instantly, nearly at the speed of light, and this field pushes the electrons in one direction around the loop. The electrons themselves move through the wire rather slowly. In fact, they drift at a snail's pace. But because the push is passed along from electron to electron quickly, the effect, the current flow almost immediate all around the loop. We can liken an electric circuit to a gentle circular stream of water. Imagine a small fountain with a pump pushing water through a closed tubing system. The water flows in a loop driven by the pump's pressure. In a similar way, charges flow around a circuit driven by an electric pressure called voltage. If we want to be calm and avoid technical detail, think of voltage as a kind of electric pressure or potential that motivates charges to move. A battery, for instance, provides a voltage. It's like a little pump that separates positive and negative charges internally using chemical energy, creating an excess of positive charge at one end and negative at the other. When you connect a wire between the battery's terminals through a light bulb, That separation of charge pushes electrons through the circuit, out of the negative side of the battery, through the wire, through the bulb's filament, making it glow softly as the electrons give up energy as heat and light, and back into the positive side of the battery. Around and around the electrons go, as long as the circuit is complete and the battery has energy. In a calm mind's eye, you could see the circuit as a loop of gentle current, rather like a quiet river circulating. The electrons are like water molecules, the battery like a pump or a hill giving the water pressure, and the lamp like a water wheel or mill that the flowing water turns. Indeed, electricity can do work like turning motors or powering devices, but in our peaceful setting, we focus on how serenely and invisibly it occurs. Unless there's a spark or a light, electricity itself is not directly visible. It's a silent, unseen flow. If you've ever watched a string of fairy lights glowing, you saw the gentle result of countless electrons moving through tiny filaments or LEDs, each electron's motion guided by the electric field in the wire and giving a bit of energy to produce light. It's important to note that while electrons move around the circuit, they do so under guidance of the electric field. When you flip a switch, you complete the circuit and the field propagates almost instantly, causing electrons everywhere in the loop to begin drifting. It's like a long tube filled with marbles. Push a new marble in one end and almost immediately one pops out the other end because the push is transmitted through all the touching marbles. Similarly, the electrons in a wire are like a densely packed crowd. Start pushing them at one end of the wire and nearly at once electrons at the far end respond and start moving, even though each individual electron moves slowly and perhaps only travels a short distance. This is why turning on a light is effectively instantaneous from our perspective. We don't wait for electrons to travel all the way from the switch to the bulb. Instead, the influence travels at near light speed, and electrons already present in the bulb's filament begin moving and heating it up to glow. It's a synchronized dance orchestrated by the field. Let's gently consider the concept of conductors and insulators. A conductor is a material that allows charges, particularly electrons, to move freely. Metals are the best examples. Copper wires, silver, aluminum, they all have electrons that can drift through the material with little resistance when pushed by an electric field. That's why wires are metal, to carry the current easily. Insulators, on the other hand, are materials where electrons are tightly bound to their atoms and not free to roam. Glass, rubber, dry wood, plastic, these are insulators, meaning if you apply voltage, almost no current flows because the charges don't move through. Insulators protect us from electricity by confining the current to the intended paths like wires and preventing unwanted flows. In our lamp example, the copper wires are surrounded by plastic insulation, making sure the current goes through the bulb and not into your hand or the table. In a calm sense, insulators are like quiet barriers that keep the electrical stream on course, while conductors are the open channels. When it comes to static electricity, like the comb or the carpet shock, insulators can hold charge imbalances in place. The charge you got by rubbing the carpet stays on you because skin and shoes and carpet are insulators to some extent. Conductors, however, quickly spread out any excess charge because the like charges repel each other and can move apart. For example, if you put a negative charge on a metal sphere, the electrons, being free to move in the conductor, will spread evenly over the surface, maximizing their distance from each other, resulting in a gentle equilibrium. Now, allow your mind to wander to a thundercloud on a summer afternoon. Far up in the sky, turbulent winds and collisions have separated charge. Typically, positive charges gather near the top of the cloud and negative near the bottom. The ground below, being oppositely influenced, might build up clusters of positive charge under the cloud. The stage is set for a dramatic display of electricity, lightning. But we'll describe it softly. As the imbalance grows, the electric field in the air becomes extremely strong enough to overcome the air's insulation. Eventually, a path of ionized air forms, and a sudden flow of electrons leaps across the gap between cloud and ground, or between clouds, neutralizing the charges in a brilliant flash of light and a clap of thunder. Lightning is essentially a giant spark, similar in principle to the tiny one you felt from the doorknob, but vastly larger. It's nature's way of balancing out large charge separations. We can appreciate lightning from a distance for its awe-inspiring power, but here you are safe, warm, and relaxed, perhaps listening to the soft patter of rain and a distant rumble, knowing it's just the grandeur of electricity in the sky doing its thing. After the flash, the air is refreshed. Lightning also produces a bit of ozone, which has that distinct clean smell after a storm. It's as if the atmosphere took a deep breath and sighed, restoring calm after the electrical outburst. From static sparks to currents in wires to bolts in the sky, electricity shows many faces. But underlying these is the simple idea of charges, electric fields, and the energy they carry. Let's reflect on how electricity relates to energy for a moment. When a charge moves in an electric field, work can be done, energy can be transferred. A battery, for instance, uses chemical energy to separate charges, storing energy in the electric field between its terminals. When you connect a circuit, that stored energy is released as charges flow and do things like heating a filament, creating light, or turning a motor. This conversion is typically gentle and continuous in everyday devices. Even in electronic gadgets, tiny currents flowing through circuits represent energy moving and being transformed, some into light on a screen, some into radio waves for wireless communication, some into heat. It's remarkable to think how controlled and harnessed electricity lights our homes and runs our devices. But in essence, it's the same phenomenon as the static shock or the lightning, just managed in small, steady amounts. As you relax here, perhaps you notice the soft glow of a lamp or the faint whir of a fan in the background. That's electricity at work, quietly improving your comfort. The electrons move silently along wires, out of sight, turning the large, impersonal forces of nature into gentle, useful effects. We should also recall that charge is conserved, meaning it isn't created from nothing or lost, it's just moved around. When you charged yourself on the carpet, electrons moved from the carpet to you, so the carpet got a tiny positive charge while you got negative. In the universe, the total amount of charge stays the same, it merely transfers from one object to another. This conservation gives a kind of balance and continuity to electrical processes. What leaves one place appears somewhere else. Let's imagine very softly the atomic scale for a moment. In a metal wire, atoms are arranged in a lattice and some electrons are free to wander. These electrons jiggle randomly all the time. Metals have electrons moving about constantly. When you apply a gentle field voltage, those free electrons gain a slow drift in one direction. They still jiggle due to heat, but now superimposed on that is a collective motion. It's like a crowd of people milling around randomly, and then a soft breeze that begins to push them so they all start moving slowly in one direction, even as they individually continue milling. If the wire is thin or long, it resists the flow more, that's resistance. Narrow or longer paths make it harder for charges to move, akin to a narrower pipe or longer hose requiring more pressure to push water through. The energy lost in overcoming that resistance is turned into heat. That's why, for example, an old incandescent bulb's filament glows. It's basically a very thin, high-resistance wire heating up from the current. But in our calm context, think of that filament just as a tiny heater that glows gently, converting the electrical energy to a warm light, like a miniature sunrise captured in glass. Before we move on, let's reinforce softly what we've learned about electricity. We learned that there are two kinds of charge in nature, positive and negative, which attract each other and repel their own kind. We imagined the field around a charge as a quiet influence that can reach out and cause forces at a distance. We considered static electricity, how rubbing or contact can separate charges and cause little sparks when they recombine. We looked at electric currents moving charges and how they flow in circuits like water in a loop, driven by a pressure difference, voltage. Conductors allow this flow easily, insulators block it. We touched on the fact that electricity is behind so many everyday phenomena, from the feel of touch to the operation of appliances. It's a fundamental aspect of our world. Keep in mind that electricity and magnetism, which we'll discuss next, are really two sides of the same coin, though it took humanity many centuries to realize that. But tonight, in this serene moment, we have the luxury of exploring both, one after the other, and appreciating how they complement each other. Let's gently shift our attention now from static charges and flowing currents to the alluring idea of magnetism, the invisible magnetic fields that can tug on a compass needle or make two magnets snap together or fly apart. We move from the domain of charges to the domain of poles, yet we will see that they are intimately related. If you're still awake and following along, feel free to adjust your position. Get cozier and let your mind's eye envision the soft, mysterious dance of magnetic fields. And if you're already drifting in and out of sleep, that's perfectly fine. The ideas will continue to flow around you like a quiet stream. Imagine you are in a quiet room, and on the table in front of you is a simple compass, a small needle balanced on a pin free to rotate. The room is still, no vibrations, no drafts. Yet the compass needle is not pointing just anywhere. One end, marked usually in red for north, is settled, pointing toward Earth's north, actually Earth's magnetic north, which is near the geographic north. This simple tool reveals the presence of something invisible, a magnetic field. The Earth itself is like a giant bar magnet with a north and south pole, and its magnetic field extends far into space, enveloping us. The compass needle, itself a tiny magnet, aligns with this field. This happens silently, gently. You wouldn't even know if you didn't look at the compass. But there it is, an unseen influence permeating the space around you. Magnetism has a slightly different feel from electricity. Where electricity deals with positive and negative charges that can exist separately, magnetism deals with north and south poles. But here's the twist. You can't have one without the other. Every magnet, no matter how small, has both a north and a south pole. If you break a magnet in half, you don't get a north piece and a south piece. You get two smaller magnets, each with its own north and south. It's as if the very nature of a magnet is a dipole, two poles together. The north and south poles attract each other, north seeks south, and like poles repel. North pushes away north, south pushes away south, similar to how opposite electric charges attract and like charges repel. However, since you can't isolate a single pole, the magnetic lines of influence always loop from a magnet's north end around to its south end, forming closed loops in space. Think of a bar magnet. Perhaps you played with one as a child or have one on your refrigerator holding a note. It has a north end and a south end. If you sprinkle iron filings around it on a sheet of paper, a common demonstration, the filings will arrange themselves into graceful curved patterns looping from one pole. Those patterns trace out the magnetic field lines. Although we can't see the field normally, the iron filings, which become tiny induced magnets themselves, line up along the field and reveal its presence. The field is strongest near the poles of the magnet, where the filings cluster densely, and weaker further away, where they spread out. Now, magnets come in different forms. There are permanent magnets, like the bar magnet, or those fridge magnets, which have persistent magnetism due to the microscopic alignment of magnetic domains, little regions inside made of iron atoms whose electrons' motions produce tiny magnetic fields that add up. And then there are temporary magnets or induced magnets, for example, that iron nail that isn't a magnet normally, but if you stroke it with a magnet or bring it near one, it temporarily acts like a magnet. And importantly for us, there are electromagnets, which we'll talk about soon, magnets created by electric currents. Let's keep the imagery gentle. Envision holding two small bar magnets in your hands on a lazy afternoon. If you bring the north pole of one near the south pole of the other, you feel a tug. They want to come together. If you bring north to north, you feel a subtle push, as if an invisible spring is resisting you. If you let go, two like poles will push each other away. It's almost playful. Magnets can exert forces without touching due to their fields interacting. Children often find it fascinating, and indeed, one can spend time just feeling that cushion of repulsion or the sudden jump of attraction. It feels almost alive, but it's simply the magnetic field in action. The Earth's magnetic field, as we mentioned, is relatively weak on the surface, much weaker than a typical fridge magnet, but it's enough for navigation. Many migratory animals, like certain birds and sea turtles, have a sense for Earth's magnetism. helping them find their way across vast distances. Imagine a sea turtle calmly swimming thousands of miles, guided in part by an innate feeling of the Earth's magnetic contours, a slow, natural guidance system. How gentle and wondrous that such a subtle field can influence living beings. Now, magnetism and electricity are deeply connected. For a long time, they were thought to be separate phenomena, but in the 19th century, experiments revealed the connections. It was discovered that moving electric charges create magnetic fields. The first hint came from a Danish scientist, Hans Christian Ørsted, who in 1819 noticed that a compass needle deflected when placed near a wire carrying an electric current. It was a surprising observation. A steady electric current, charges flowing in the wire, produced an effect on a magnet. This told the world that electricity could produce magnetism. Shortly after, others like André-Marie Ampère studied how currents produce magnetic fields in space. For example, a straight wire with current generates a circular magnetic field around it, like invisible rings encircling the wire. You can visualize it by imagining grasping the wire with your hand. Your thumb points in the direction of current, and your fingers curl around. That curling direction is the direction of the magnetic field loops around the wire. This is a gentle rule known as the right-hand rule, but no need to memorize. Just picture the field swirling around a flowing current like a soft vortex. If we coil a wire into a loop or many loops, the magnetic field through the center of the loop strengthens and looks similar to the field of a bar magnet. In fact, a simple coil of wire with current running through it becomes an electromagnet, with a north and south pole just like a bar magnet. This is the principle behind so many devices: electric motors, transformers, MRI machines. They all use magnetic fields created by currents. But let's stick to a simple, calm example. Imagine a metal nail wrapped with some insulated copper wire. If you connect the ends of the wire to a battery, current flows through the loops around the nail, and suddenly the nail becomes a magnet, only while the current flows. You can pick up paper clips with it, for instance. Disconnect the battery, and the magnetic effect fades. The nail might retain a tiny bit of magnetism, but not much, unless it's a material that stays magnetized. So here we have a controllable magnet, one powered by electricity. Conversely, it was also found that moving magnets can induce electric currents. Michael Faraday, an English scientist, demonstrated in 1831 that if you move a magnet in and out of a coil of wire, a current is induced in the wire while the magnet's field is changing through the coil. If the magnet is held steady inside or near the coil, no current flows. It's the change, the motion or variation, that matters. This is called electromagnetic induction. Picture a small coil of wire connected to a sensitive galvanometer, a device that shows current with a needle. Move a bar magnet towards the coil. The galvanometer needle flicks, indicating a current. Pull the magnet away. The needle flicks the opposite way, indicating a current in the opposite direction. This happens because a changing magnetic field creates an electric field in the conductor, pushing charges around the circuit. Essentially, a moving magnet or a changing magnetic field is like a hand that nudges the electrons in the wire. Now think of this in a very gentle, grand context. In a hydroelectric dam, massive turbines spin magnets past coils of wire to generate the electricity that lights our homes. But we can shrink that idea down to something as simple as a bicycle dynamo, those little devices that rub on your bike tire to power a headlamp. In a bicycle dynamo, the wheel's motion turns a magnet inside a coil and produces current that lights the lamp. The faster you go, the faster the magnet spins, the more rapidly the magnetic field through the coil changes, and the more current is produced, hence a brighter light. It's all the same principle Faraday discovered, put to practical use. But whether it's a giant turbine or a tiny bike light, the underlying process is silent and invisible, moving magnetic fields creating electric currents. So we have this beautiful symmetry. Electricity can create magnetism, currents produce magnetic fields, and magnetism can create electricity, a changing magnetic field produces current. It's a dance of two forces. This interplay is governed by fundamental laws of physics that were eventually distilled by James Clerk Maxwell, who realized they are part of one unified electromagnetic theory. Maxwell's equations, as they are known, described how electric and magnetic fields propagate and interact, and led to a stunning prediction. There should be electromagnetic waves, oscillating electric and magnetic fields that travel through space. And the speed of these waves, calculated from the known electrical and magnetic constants, turned out to be about 300,000 kilometers per second, which was already known to be the speed of light. This was the eureka moment. Light itself is an electromagnetic wave. The gentle glow of a candle, the rays of the sun peaking at dawn, the twinkle of stars, all are manifestations of electromagnetic waves, a self-sustaining combination of electric and magnetic fields moving together through space. Let's digest that slowly and serenely. We started with mechanical waves like water and sound that need a medium to travel. But here, electromagnetic waves do not need a medium. They can propagate through the vacuum of space. They are vibrations, but not of material. Rather, they are vibrations of the electric and magnetic field, one feeding into the other. How can we imagine this calmly? Try picturing the following. In space, at some point, an electric field is increasing and decreasing rhythmically, and at right angles to it, a magnetic field is also increasing and decreasing in sync. These fields sustain each other. A changing electric field produces a changing magnetic field, and a changing magnetic field produces a changing electric field. Together they form a wave that travels. If you could see it, which ironically, if it's visible light, you are seeing it by definition, it would look like a pair of perpendicular waves, one electric, one magnetic, moving along at the speed of light. Think of gentle ripples, not in water, but in the very fabric of the electromagnetic field filling space. When you tune your radio to a quiet music station, the antenna is picking up invisible radio waves. These are low-frequency electromagnetic waves and converting them to electrical signals, then to sound. When you warm yourself near a fireplace, you feel infrared radiation, electromagnetic waves of a slightly lower frequency than visible light, carrying heat from the fire to you. A rainbow separates sunlight into its frequencies from red, lower frequency, longer wavelength, to violet, higher frequency, shorter wavelength. But all of those colours are electromagnetic waves, differing only in frequency wavelength. Beyond violet, we have ultraviolet light, which we can't see but can redden our skin, then even higher frequencies like X-rays and gamma rays. Below red, we have infrared, then microwaves, which warm our food by agitating water molecules, then radio waves, which carry information across cities and continents. It's all one grand spectrum of electromagnetic waves. And here's the enchanting part. They all travel at the same speed in vacuum, the speed of light, only their frequency and wavelength differ. In a vacuum on a dark, clear night, whether it's the glow of a star, visible light, the broadcast from a distant radio tower, or the radar pulse from an observatory, all these electromagnetic waves crisscross space silently, passing through one another, spreading out, some eventually reaching your location. Right now, your environment is likely permeated with radio waves from Wi-Fi or cell towers. The room is bathed in light, if not visible, then perhaps infrared from warm objects. And through the walls, maybe distant radio broadcasts are coursing. None of this disturbs your rest. It's just a subtle background of activity that our senses mostly tune out except for light and warmth. Returning to magnetism itself, aside from the dynamic relation with electricity, magnets have their own steady presence in our lives. Perhaps you have something like a soft magnetic clasp on a journal, or a magnetic latch on a cabinet door that clicks gently shut. These are benign uses of the fact that magnets exert forces. The Earth's magnetic field, as mentioned, quietly shields us from some of the charged particles streaming from the sun, the solar wind. Those particles get guided by Earth's field toward the poles, colliding with the atmosphere and producing the beautiful auroras, shimmering curtains of green and pink light that dance in polar skies. The aurora is like a gentle nighttime ballet produced by charged particles and magnetic fields, a lovely reminder of Earth's magnetic embrace interacting with the wider cosmos. Now, let's imagine the interplay of electricity and magnetism in a more down-to-earth scenario, an electric motor. This may sound technical, but we'll break it down simply. In essence, a motor converts electrical energy to mechanical motion using magnetism. Picture a loop of wire, an electromagnet when current flows, placed in the field of a permanent magnet. When current goes through the loop, it becomes magnetic and is either attracted or repelled by the permanent magnet's field, causing it to spin half a turn. Cleverly, motors switch the direction of current every half turn using a commutator or electronics, so that the loop keeps being pushed around in the same direction, spinning continuously. All of this can happen smoothly and quietly. For instance, a fan on a low setting hums softly as its motor spins, driven by electromagnetic forces. You can almost feel the magnetic fields doing their delicate dance, pushing and pulling to keep the rotor turning. And in reverse, if you spin a motor's shaft yourself, the motor will act as a generator, which is how those bicycle dynamos or hand crank flashlights work. Mechanical motion is converted back into electricity by the changing magnetic fields in coils. It's a harmonious symmetry. Electricity can make magnets, and moving magnets can make electricity. Our modern world harnesses this in countless ways, yet here in the stillness of your room, these processes continue quietly without demanding your attention. They simply ensure your comfort. For example, the power station far away might be using rotating turbines, magnet plus coil, to send electricity to your home, which a transformer, another application of induction, using coils and changing magnetic flux, steps down to safe voltages. And finally, it arrives to gently power your bedside lamp or white noise machine. Let's gently recap what we've covered about magnetism and its connection to electricity. We learned that magnets always have two poles, north and south, which attract or repel one another. We envisioned Earth as a giant magnet guiding compasses and possibly even animal migrations. We saw that electric currents produce magnetic fields, the basis of electromagnets, and changing magnetic fields produce electric currents, the basis of generators and transformers. We recognize that light and other forms of electromagnetic radiation are essentially waves of electric and magnetic fields traveling through space, tying the concept of waves from the first part to electromagnetism here at the end. In short, we've journeyed from mechanical waves through static and current electricity to magnetism and then to electromagnetic waves, light, which is a beautiful full circle because light as an electromagnetic wave is also a wave, linking back to our starting point. Everything we discussed, waves, electricity, magnetic fields, is part of the grand tapestry of physics, the rules by which our universe operates. But beyond the science, there's a philosophical or soothing aspect to it. The world around us, even at its most fundamental level, is dynamic yet orderly. Waves oscillate with rhythmic grace. Charges and fields interplay like partners in a silent dance. Magnetic and electric fields weave together to send light across the cosmos. There is a deep harmony in these phenomena. They obey laws that are complex in detail, but simple in principle. And those principles manifest in gentle, accessible ways in our everyday experience. A boat bobbing on ripples, a balloon sticking to a wall after being rubbed on hair, a compass needle calmly pointing north, the warm glow of a light bulb at dusk. As we near the end of this journey, allow yourself to feel a sense of connectedness with these natural phenomena. The very atoms in your body are held together by electromagnetic forces. The light by which you might read or navigate your room at night is an electromagnetic wave. The sound of this voice reaches you through waves in air. If you have any electronic device playing this audio, it operates through electrical currents and fields. We are truly bathing in these processes. Yet they are not hostile or alien, they are the normal workings of the universe and have been since the beginning of time. Every star is a massive ball of plasma where electric and magnetic fields rage, but also from which calm light waves travel across space. Every gentle ocean swell follows the same physics as any wave, a balance of inertia and restoring forces. Now, as you settle deeper into comfort, let's slowly wind down by revisiting the calm highlights one more time, in an even more lulling, simplified way to send you off into sleep. Waves. Picture once more those gentle ripples on a pond. They rise and fall in a steady pattern. They remind us that energy can move gently through a medium. No water is permanently carried away, it's just a passing form. The wave has a rhythm, like your breathing, like a heartbeat, like day turning to night and back to day. Rhythm and repetition, waves embody that. Think of the soft whoosh of distant ocean waves arriving at a beach, in and out, a natural lullaby that many find ideal for sleep. In your mind, perhaps you can hear those distant waves now and feel yourself rocking ever so slightly with their cadence. Electricity, now imagine that subtle tingling energy that can either stay still as static or flow as current. We have the image of a warm lamp glowing with a steady golden light. The lamp's light is fed by electricity, but you don't see the electrons or feel anything except the light and maybe a bit of warmth. It's as if by magic that power travels through a simple wire to produce comfort. Electricity also reminds us of balance, positive and negative, giving and receiving. When there's imbalance, nature gently corrects it, sometimes with a spark, but often quietly. Even within our own bodies, tiny electrical signals in our nerves carry messages. Our hearts beat due to electrical impulses, a natural pacemaker. We are, in a sense, electrical beings too, but all nicely regulated and typically unnoticed by our conscious minds. So electricity is not foreign, it's part of us and our world, usually calm and controlled. Magnetism, recall the compass or the bar magnets. Think of the soft pull you feel when a magnet tugs on a piece of metal, like when a fridge magnet clings to the door with a satisfying gentle tap, or the way a collection of paper clips might dangle from a magnet, all clinging together. It's a quiet force, often steady. A magnet sitting on a fridge doesn't make noise or anything, it just sticks. Magnetism gives us a sense of direction, literally for navigation, and a sense of coherence, those field lines looping around, connecting north to south. It's like an invisible thread sewn through space, keeping certain things aligned and in order. And when magnetism and electricity dance together, we get marvelous outcomes like motors that whir and light that shines, all making our lives easier. Finally, the electromagnetic waves. The fact that light itself is a wave made of electric and magnetic fields is an elegant capstone. It means that the gentle light in your room or the silver glow of moonlight spilling through the window is a wave too. A wave that travelled perhaps from a bulb or from the moon's reflected sun rays, taking less than a second in the case of your lamp, or about 1.3 seconds from the moon. That light has no mass, it's pure energy moving through the great cosmic field. And when it touches your eyes, it allows you to see, or if it's infrared, it simply warms you. How benign and nurturing light can be, just the right amount lights our days, and when lower at night, signals our bodies to rest. So we have woven a story from waves in water and air, to the charges and currents that course quietly through matter, to magnets and fields, invisible yet influential, and ultimately to light, an electromagnetic wave bridging it all. It's time now to let go of the specifics and allow your mind to drift wherever it wants. You might find these images floating in and out, a boat bobbing on calm waters, a glowing filament in a vintage lamp, a compass needle lazily turning, a slow wave of northern lights under a starry sky, all these and more gently cycling in your thoughts, lulling you deeper into tranquility. You are safe, you are relaxed, and you are connected to the fundamental calm rhythms of nature. Every breath you take is like a wave. Every beat of your heart is like a signal in an electric circuit. Your body even has its own magnetic fields, tiny but measurable with sensitive instruments and bioelectric currents. In a way, you are a living harmony of waves, electricity and magnetism, all working together quietly to sustain you. Feel the weight of your body supported by the bed or chair, the electric forces in the materials holding you up firmly yet kindly. Feel the air entering your lungs. Pressure waves of sound might be distant in the background, but none disturb you now. Your eyes, whether closed or softly open, might sense only dim light at this time, as the world itself grows quiet and dark, preparing for rest. As we conclude this gentle exploration, I will leave you with a soft affirmation of the peaceful nature of these physical phenomena and a few repeated soothing points to help you drift away. Waves are gentle and repetitive. They teach us that energy can flow without effort. Electricity is balance and connection. It quietly powers the warmth and light in our lives. Magnetism is guidance and invisible strength. It keeps things aligned and offers subtle forces that shape our world. Together they unify into a beautiful, coherent picture of how our universe moves and interacts, largely unseen but always present, like a calm undercurrent beneath the surface of everyday life. Now you can let all these thoughts fade as you settle into the comfort of knowing that the universe, at its core, is rhythmic and ordered, and you are part of that order. Everything around you is moving in tiny ways, atoms vibrating, Earth's field flowing, and yet here, in this moment, it all feels still and quiet, because the motions are either too small or perfectly steady. It's like being cradled in the arms of physics itself. The same laws that cause a breeze or a wave are cradling you with gravity on your bed, with electromagnetism keeping you warm under your blanket, with the sound of my voice tapering off to a whisper. You are drifting now, floating on calm waves of thought. There is nothing else you need to do, nowhere else you need to be. Just rest, secure in the knowledge that the waves will continue to ripple. The electric currents will continue to flow, and the magnetic fields will continue to enfold the world, all as you sleep soundly. When you wake, they will still be there, reliably doing what they do as they have through all of time. Feel your breath once more, like the tide. In and out, in and out. Slow and peaceful. Let any remaining tension in your body sink away, drawn out like an ebbing wave. Your mind can be as light as a cork on water, bobbing gently, eventually coming to rest. Thank you for allowing me to share this quiet journey with you. May your dreams be filled with gentle waves, soft light, and a sense of the deep, soothing currents that underlie reality. You are part of this gentle flow, and you can surrender to it now, floating safely and easily into the sea of sleep. Good night.